recall some parts of what sir told, and then we'll go into the Python implementation. So I've taken this slide from the internet, so you can.
Uh,
I'll share it. Yeah.
Suman, little louder.
Okay, right, sir. Yes, sir. I'll check the volume also. Yeah. Okay. So yeah. So actually, steganography is that normally, for example, we have images, we have audio, we have videos. After we add some data into the images or audio, what happens is like we don't want anyone to detect the that we have actually added it. For example, say I have an image of a rose or image of a person, and then I try to add some data into it. Then I don't want anybody to actually know that the data is there in it. In the brief sense, this is what steganography is. So let me go forward, and this all this is yeah. So check this out. So this is the carrier file. So assume this to be the image. Now I have a text here. So when I actually add the text inside this image, still the image is the same. So there is no difference. So as a human, I cannot distinguish between the actual image and the image with the hidden text. So in the brief sense, that's what it is. So when I say it is image steganography, or when I'm talking about audio steganography, it means that the carrier file is image, or the carrier file is an audio, or the carrier file is a video. So yeah, so carrier files. So I was talking about this part only. So in case if it is a JPG, so if it is an image, then we can talk about JPG, or if it's a video, then if it's an audio, then it's wave format or MP3. So in that way, we can actually hide the uh, hide the data or hide the secret message into different uh, audios and videos and all. Yeah, yeah. So many of the people have already put in effort and built steganographic tools. So these tools actually will help in actually they're like ready-made tools to use, and they have already coded the all the logics in it, and they give you the graphical user interface, and we can actually import our image, put the text, and download it. So if I actually, for example, if I go and open stag hide, then it gives me a beautiful interface, and I can upload my audio file, and I can upload my text, and it will give me the audio, and it will use some technique, some logic, but which is hidden to me. But the audio file which contains the text will be similar to as how it was before. So yeah, if any questions, you can stop me anytime. And yeah, so let me continue. So yeah, you can refer to many of the popular sites and you'll get it. Okay, so let me go to the algorithm. Yeah, so the other part is steg analysis. So just like how we try to hide the data inside the audio or inside the image, many people like attackers or any people, they want to know if the data is actually there, and how do I retrieve the data without actually knowing the process of embedding of how the message has been embedded in the carrier file. So that is called steg analysis. So this analysis is actually to measure the strength of the steganographic algorithm. So that is what it is. So here I do the histogram analysis. All these are different types of attacks. So we are trying to measure the robustness. If I take an image, I'm trying to measure the robustness of the image. So when I try to attack the image and try to get the secret message or the hidden data outside, I'm trying to measure the strength. So stag analysis deals with how to break the system. Yeah, and of course my goal will be to get good accuracy, be consistent, and yeah. Yeah, of course, did it? Yeah. So, of course, by seeing just by seeing, if I just see the image, of course, I mentioned that as a human, I'm unable to distinguish, and that is the main goal of steganography. So, if I'm failing in that sense, then steganography is not implemented properly. So, yeah, that is the smallest or the I can say it's not an attack, but it's like failure in the implementation of the algorithm, because as a steganographic algorithm, I need to make sure at least the visual perception should be good. In the sense, when I see the image, it should be similar to the actual image or the source image. The modified image, which contains the hidden text or the secret message, is called the carrier image. And this is the term. This is just the terminology. And yeah, these are all different attacks. And let me go straight to the simplest algorithm. These are all the tools I was talking about it. So let's see one tool. So let's say it is TextSpy. So it says, yeah, just choose an, yeah, you can just see the user interface and just hide the, put the text here and put the file. And yeah, so these are the tools. And yeah, so now let me just give you a small sense as to what is the relation between these two terms, one here and one here. So in cryptography, if I have a text and I encrypt it, so everybody or the attacker, whoever intercepts the text, he actually knows that the text has been encrypted, because the text actually will be completely sort of a garbage. So I can't make any sense of it. So that is cryptography. So in cryptanalysis, we know that okay, the message has been encoded, and we try to break or measure the strength. So any kind of analysis like crypt analysis or steg analysis is to measure the strength. So in the sense, if steg analysis is measuring the strength of the steganographic algorithm, then crypt analysis will measure the strength of the cryptographic algorithm. So cryptography is not in this sense, in this part, but yeah, they both are similar, doing the analysis to measure the strength. And cryptanalysis is not in the part. So let me move forward. And of course, this brute force in steganography everywhere, just the blind search, trying to take different parts of the pixel. And let me just go forward. And let me show you the algorithm now. Okay. Okay, so let me now go to the algorithm part. Okay, so I'll just type it here. And is my screen visible still? Hello?
Yes,
Is my screen? Yeah, thank you. Okay. So yeah, so the simplest algorithm or the steganographic simplest algorithm is called the LSB encryption, LSB algorithm. And when we actually add it, so I'll just write LSB algo. Okay, first let's write the algorithm. Okay, let's see. It's very small here. All right, I'll write it here only then. Okay, fine. Let me just write it as a paragraph here. And yeah. Okay, so what we're doing here is we're taking the image and we actually want to hide the data. So let's say some message. Let's say DF, digital forensics is the message. So this is just the text editor. So this is not the Python. I'll go to the implementation. I just want to discuss the algo. So let's say now this is the text, digital forensics, and I want to embed this text. Okay, so what LSB algorithm says is, now in an image, now how is an image represented? So image in general is represented as a array of pixels. So let me try to increase the font because I need, just give me a minute, 1 minute. It's a new software I downloaded. This is not good. Okay, all bold. Okay, yeah. Okay, I'll make it big. Okay, after I type. Yeah. So what I want to do here is, now say image is a collection of pixels. This is what I'm talking in the spatial domain. So image can also be represented in the frequency domain. So this LSB algorithm, which I'm going to discuss, is the simplest algorithm to actually embed the information inside an image. So this is for the image. I'm talking about image. Okay, this is for image. Now coming to the algorithm. So now, as I mentioned, image is a collection of pixels. So for example, if I have an image of 512 cross 512, let's say it's a 512 cross 512 image, then I can comfortably say that the total number of pixels are 512 into 512. So you can think of this image as a two-dimensional matrix. So now you got this, right? Let's think of the image as a two-dimensional matrix. So every cell, the row column, every cell is a pixel. Now let's say the pixel value is, okay, yeah, as I mentioned, the pixel value, let it be 126. So I represent 126 or let's say 128. So I represent 128 in binary. Okay. Okay. Yeah, 2 power 7, right. So 128 is in binary. Now, as a human, whether the pixel value is 128 or the pixel value is 129, it hardly makes sense when I actually plot it or when I actually view it as a color. So I'm talking about a grayscale image. You can even talk about a color image. So yeah, let's talk about the grayscale image. So whether it is 128, even Dipankar sir has mentioned this. So it's 128 or 129. It doesn't make difference for me. As a user, as a human, my eye cannot catch a smallest bit. So this algorithm makes use of that. So I want to add the data in the last bit of the pixel value. So say my data is digital forensics. So I have to make sure I have to find a way to encode this digital forensics text into bit pattern. I can use the popular ASCII code or any other code, but I need the bit pattern because everything is stored in binary. And even if it is not stored in binary, I need to change the bit value here, 0 or 1. So I need to convert this to a bit pattern. Let's say I'm using ASCII value. Now, coming to, let's say the ASCII value for this whole text is something. Okay, and we know that ASCII value range is from 0 to 255, and the pixel value is also 0 to 255. Okay. Now, so each character will be of 8 bit. So I need 8 pixels, and I will change the last bit. So what I'm trying to say is, let's say the pixel value is 128, and my data, the first bit of my data, D. So D in ASCII, say ASCII A start A 65. So B is D is plus 3, 68. So that's 68. 68 when I present in binary, so it is 64 and 4. Yeah, 68. So I need to add. So I just keep traversing through the pixels. I just traverse the matrix and add the data. First bit is 0, right? So I leave it as 0. And let's say next pixel value is 12. But the next bit is 1, right? So I make it 13. In this way, I know that the last bit, when I actually extract it, do the ASCII conversion, the data actually makes sense to me, but nobody knows that that is the data. That is the LSB algorithm. So any questions? No, still here. Any questions? Okay. So if there is no response, I'll move forward. Okay. I'll close this. It's not required anymore. I'm still audible, right? Hello?
Yeah, you're audible.
Yeah, thank you.
You're audible.
Yeah. So let's implement the algorithm. So first thing is to, okay, I'm now just using Python here, and I'll start. So first let me read the image. So let's code from start, because if I show you the code, you won't make sense of it. So I'm coding from starting. It'll take hardly 10 minutes, but just follow along. So let me read the image. So any library related queries, like I'm using OpenCV, of course, to read the images and display and all those things. And I'm using matplotlib and other libraries. Library related functionalities, you need to look into the documentation. Algorithm related, you can ask me. I'll help you. So yeah, I imported CV to top. So I'm reading the image, and I want to read it in grayscale mode. As I mentioned, if I'm reading it in RGB mode, then what happens is okay, what happens is I get RGB, so 3 matrices. So it's an n-dimensional, it's a tensor actually. So every matrix, it's a 3 matrices of 512 cross 512. I'll show you that, no problem, I'll show you that. So I'll remove this and let me see the image name. So cover1.png. Okay. Okay. Let me import here only. I'll just run it. I'll just run this part. Okay. Yeah. Don't worry about the top thing. So it's just to, I should not make any mistake, right? Yeah, don't worry about the warnings. Okay, so I just read the image. Now I'll show you the image. Let me check something is wrong here. Cover underscore one. I'm sorry. Yeah, sorry. I'm sorry about that. So yeah, so this is the image, and I've read the image through OpenCV. Now let me just check the. Let me show you the. It is 256 cross 256 cross 3. So there are three matrices. There are three matrices of 256 cross 256. So I'm operating in grayscale mode, right? So now I need to use for this. Okay. So now I'm operating in one dimensional mode. So everything is a pixel value. So let's print the pixel values. Okay. So let's take row and column out. Okay. Okay. Now let me show you some pixel values. It's just a two-dimensional matrix traversal in Python. Okay. Okay. So what I'm saying, what I'm showing you here is actually the pixel values, all the pixel values. Okay. There are a total of 256 into 256. So 2 to the power of 16. So 64,000 pixels. 64,000 pixels are there here. Okay. Now, okay. Yeah. So now what I have to do is I have to make the text. So let's say my secret now secret, right? My secret is, let's make a small secret so that I don't need to stress so much. Let the secret be, say my name. Okay. Okay. Or let it be little digital forensics. Digital. Yeah, that will do. Okay. So let's print the secret. Okay. Now what I have to do, what as I mentioned, the algorithm, I need the bit pattern. So I have to convert the secret to a bit pattern so that I can actually embed the pixel in the pixels, right? I need this bit pattern. So I'm taking each, so this is each character. I'm taking each character, okay? Now I need to convert this to bit pattern. So let the bit pattern, okay? I need the ASCII value. So I think this should work. Okay, 1 second. Okay. Let me check what's the way to get the ASCII value. Let me just think. Okay, let me just check what I have done for ASCII value. Okay. Yeah. So let me use this function. I'll explain what it is. Okay. So I need to make sure I'm not making a mistake. So let me just paste the function here. So it's taking the decimal and converting to binary string. Okay. Okay, I don't want this one. I want the ASCII value one. Yeah, char to binary string. This one. Okay. I want this function. Okay. Yeah. So what it's doing, it's taking a character and it gives me the binary string. So let's test this actually. Let me call this function. This is all I've written the functions. So you can just use A. So this is 65. I told you, right? A is 65. 64 plus 1, 65. So when I call this function, I get the bit pattern. Okay. So this is the format to actually convert it. You can check this. You can check this in Python. This is a way to actually convert it. So order. This is the way to get the ASCII value. So ORD. So in C++ it was int, but here it is ORD. Okay. So I got the ASCII and I'm converting to binary straightforward, right? Divide by 2, and that is already there in the format function. Okay. Now I want to convert. This is the char, right? Each char. For each char in the secret, I want to get the bit pattern, right? So let me just call the function with the char. So what's happening? It's actually combining all the string. Okay. So n, spelling mistake. Okay. Okay. Let me print this bit pattern. So this is the actual ASCII code of actual bit pattern of digital. So let's change it now. Let's make it space, or let's add more characters. Forensics. Okay, this is digital forensics. I want to keep the text start so that okay. Yeah. So I get the bit pattern of my message. This message I have to embed successfully in this image, and the image quality should be undistorted. Okay. Yeah. So now, as the algorithm, what I mentioned, traverse to each pixel, apply this bit pattern, right? Okay. So let's copy this same thing here. This traversing each pixel. So let's make the algorithm a little bit simple here. So let's say the first I just append all the pixel value, all the bit pattern in the first pixels. I can use any logic, either like this or appending in the center. I can add the data in these pixels. So I'll show you how to add it, and it's up to you to choose the region where you want to add it. Anywhere you add, one bit change to the pixel value will make no difference to the eye, and there's no way anyone can find it. Okay. Okay. Coming to this, let me keep a count. Let me keep a count, and let me get the bit by bit pattern. Okay. So I'm incrementing it by 1. So I got the first bit. Now I need the first pixel value. Okay. So pixel img I comma j. I showed you here. I got the pixel value. Now the heart of the algorithm. So let's do something here interesting. So let me say I have 128. Okay. And if I XOR with 255, it should be okay. Is this XOR or okay? So let me just go to this part here. So what I'm saying is I want to change the last bit, right? Instead of actually changing the last bit, if I take 127 and not XOR, I'm sorry. It should be or yeah or. So when I take or 127 with all ones, or XOR, let me just think. Okay, anyways, let's avoid this logic. Okay, so let's take the last bit and change it. So I got the pixel value, and this pixel is a decimal pixel, as I showed you in the print here. So let's convert this to binary, and let's convert decimal to binary string. So I'll just show you this function how it does. So 10 is 8 plus 2, right? So let's avoid the XOR thing. Okay, let's call this function and decimal to binary string, and let's pass the pixel value. It will return the binary string, and then okay, let's take the whole value. Yeah. So this pixel is the actual pixel binary. Okay, I got the binary string, and now I want to change the last bit. The last bit, so I can use the negative index. So what I'm doing here, I'm using the last bit. I'm changing the last bit to bit. I want to add this bit. So I'm assigning it to this bit. And now I have the pixel changed to with this bit. So I need to actually take this pixel and replace with the original one, right? So img I comma j. So pixel binary, I need to convert to decimal again. Okay, decimal to binary string. Let's pick the function up. No need to write all those things here. So binary string to decimal, straightforward int, calling with 2. Okay, yeah, let me pick this up. Okay, so this is the, let's use the function. Let's keep it here. Okay, so I take the binary string and I'm converting to decimal. So let's take this pixel binary and I'm assigning back to image. Okay, so with this I don't need to traverse the whole thing. I know the bit pattern. So whenever the count, okay, let me just think, count 1, if count is equal to img decimal 2. Okay, let's run this first. Okay, let's print bit here. Okay, bit pattern of count. Okay, so yeah, so what I'm doing here, I just take the bit pattern one by one. I'm picking the bit and then I'm taking the pixel, converting to binary, converting the binary pixel back to image. Here I need to change the binary pixel value. So I take the binary pixel value and then I append the last bit with this. Then I pass it here. I think there's an item assignment. Okay, then how will I change it? I should get the, okay, let me just, okay, okay, I need to just okay, let's pick this up. Let's take this. Okay, indexing this should work, right? Okay, let's print. Okay, I think now I need to use the XOR function. So when I take, or let me just no, not this one. Okay, I need to assign the last bit. So you got what I'm saying, right? I need to change this bit to the actual bit and keep moving forward. So the str is not supporting this. Let me just think what to do. This guy has told something. What he has told? 6 to 12 list. Okay, but it should work, right? Okay, let's. Yeah, I got it. I got it. So len of, so I got this idea just now. -1. Yeah, okay. The error is solved, I think. I was just going, not looking properly. Yeah. So it's pointing at this part now. Okay. So I need to stop correctly when this count finish, right? So for just, let me just use this as a simple algorithm now. 56. Okay. I'll just break. Okay. First 56 pixels, because let's assume the text is fixed here. Okay. And if count equal to 56. Okay. Break. Okay. Okay. So data is there. This is the encoding algorithm. Now let's print the image. Let's print the image CV2. Yeah. No. I just need to plot it, right? I need to read the image. So what was the image name? IMG, right? Okay. After putting the message and before putting the message, there's absolutely no change. So now we can take this any complexity. I just increase the text value here. I run it. I get a bigger bit pattern, 272. I'll put this to 272. We can automate this also, right? You got how it. So I just get no change. Okay. This length we can actually use some delimiter to actually find out where the text, or we can just keep something, or we can use any logic here. Okay. So I'm just assuming that I know the length before, and even if I don't know the length of the message, if I take it as an input, I can then read the input length, right? If I just say I want to take the instead of secret, so let's say I want to take secret as input. So let's say I want to see input. So let's comment this. It's changed, right? It still runs, but I need to change this. So I'm getting the length, right? Length of secret. Let me make this as breakpoint. Length of bit pattern. Okay. Yeah. Now over, right? So let's run it from here. The algorithm. So read the image, check the size. Okay. Enter the secret. Uh, Bit pattern of the secret ASCII. Length encoded in the image. Reading the image. So let's pull the text back, and we are done. Okay. Let me just pull the text out now. Let's again iterate through each pixel, and just the reverse process. If count is breakpoint, then break, and I don't have this, right? I have the pixel. So read the pixel, convert to binary. These two are same. Am I audible still, or this time just talking? Hello?
No, you're audible.
Yeah, thank you. Okay, so I just convert to binary. Now, yeah, now this is a very simple one, right? I convert to binary, and this is the message decoded. Let's make it now bit pattern. Bits. Choose camel case. Message decoded bits. So let's take the last one. Okay. Negative index. Done. And let's print it. Okay. Something mistake. Pixel and binary. Take the pixel, convert to binary string. Okay. Sorry. No. Convert the pixel to binary. Okay, let's print this pixel binary. Why is this not even running? Okay. Breakpoint is already. No. Okay, count is already up, right? So let's make count to 0 again. Yeah. So I think now it should work. So this is the, I think it's still running. It's going to infinite loop. Okay, let me just see what mistake I made. If count is equal to, okay, I'm not incrementing the count, and count is always 0. Okay, so breakpoint is fixed, and after I add each thing, I need to increment the count. Okay, and I don't need to print this. Okay, over. I got the message back. Let's convert this to English sentence. So let's pick the function. I think I have a function ready. Okay, not this. Decimal to binary, binary string to decimal. Let's pick one nice function from top. Binary string to English sentence. Okay, this is nothing. Just it's taking the first 8 characters. Okay, converting into characters, and then it's converting back. Okay, just grouping it to 88 bits, converting to ASCII int, converting that int back to character. So 8 bits, 8 bit to int to ASCII to character, and let's run this. Okay, let's copy the name. I ran it. Okay, this is keyboard shortcut, and now let's do this. I got my message back. Okay, this is the LSB encryption. Let's do it again. Let's use my name. Okay, bit pattern. After encryption, after encryption, after adding the text. Okay, I'll stop here. Okay, so any doubts? Yeah. So in this way, we can actually use any algorithm, go to any extent, and add the bits, uh, add the data anywhere in the image, be it the center, corner, straight, left, right, based on the logic that we choose. I've added the first, so you can add it as the last. You can add delimiters to make the variable length, and yeah, and if you want to, this is the spatial domain. We have actually used the LSB encryption. If I want to use the frequency domain, then I have to use the DCT. Then there must be proper algorithm. So based on that, we can add it. And yes, sir. That's it, sir. Thank you. I'll stop here.
Suman, you can tell something, the basic idea behind the audio.
Oh, audio, sir.
Putting
Okay.
some message in the audio.
Okay, right, sir. So just like
The
the image.
no details.
Yes, sir. The coding part or just the intro? It's the intro, right? Should I show the audio?
Yes, so give the
Should
basic
I?
idea.
Yes, sir.
Sorry,
Okay, right.
what do you want?
No, sir. I'm saying that should I actually show some audio code, or is it sufficient to mention how it is done?
I mean, if it is simple code is there, you can show it. Otherwise, you just mention it.
Right, sir. I got it. I'll
Because
show it, sir.
now that the basic idea is clear, so
Okay, right, sir. I got it. Okay, so just like okay, I'll just show it. Why to speak? Let's go to audio. Okay, so let's use some. Okay, so just like there, I need to actually read the audio. Use the same algorithm. Okay, so let me just pick the reading function, and okay, I'll just pick the read function. Read audio. Okay, read audio. So just run all this part so that everything is clear. Okay, so this is the audio part. Okay, it's pulling that out. Okay, let me just use number of bytes, 16 bytes, and it's running. Yeah. Okay, so let me just do it here. Okay, so I have the audio file here. This is the audio file. So let me just read the audio file. Steg underscore audio. So .wav is just yet another format like MP3 or any other format. and it is more of a bigger size but a higher quality than MP3, and it is not that much used in terms of exchanging with anyone or using it in practice, but yeah, it is used for keeping the quality high, and it is yet another format that is good enough to know. Okay, let me just. Okay, it's a wave audio file. Okay, so what this function does is it reads the wave audio, and you can actually get the bytes. So I can actually get the wave audio signals, the signals that I have, like just like this, like a cosine wave or a sine wave, in terms of bytes. And once I get the bytes, just like how I showed you, the image LSB part, exactly we can do the same thing for audio LSB. So let's see what we have done here. So if I go to, I'm reading the audio file, I'm inputting the message, I'm converting the message to, this is the message part, we don't worry about this. See this part, get frame, after I get this bytes, it is just like the LSB one. I just need to convert the audio signal to bytes. And how is the audio represented? That is not in this part, but this function, let's see what this function does. Get frame in bytes, yeah. So byte array, and yeah, so this is, let's see what this is. So this is the Python this thing, which actually converts. So actually I actually have the wave kind of a byte file. When I actually use this, I actually get the bytes. So let's use this and see how the bytes look. Okay, let's use this. Okay, it's not here. Okay, it's taking time. Yeah, this is the byte values. So this is the whole audio converted to bytes. So an audio, one signal will have thousands of bytes. So let's see the length of this. It will be in thousands. Because, okay, wait. What happened? Okay. It's printed. No, it can be great. Okay, I'm not returning it yet. Printed. Okay, let's print here only. Okay. Okay, yeah, I'm printing there, right? Don't worry about this. Okay, so it is total of 1000, 10,000, 10,000, 71 lakh bytes. 71 lakh bytes. So this small audio, 59-second audio, this is 10-second audio. So I don't want to play it some song audio. So it is total of 7 lakh, I think 71, okay, whatever. This was big bytes. So after I get the bytes, I just need to add I just need to add, same there, I can follow the LSB part. For audio, there are different techniques, like there are some pulse code, there are different discrete frequency, there's many techniques to actually embed it in these bytes. But the algorithm remains the same. Like we just need to change the lower part where there is less, it is more robust, and the quality of the file remains, as well as there is less degradation of the quality. So why did we change the LSB? Because LSB has least impact, and the human perception can hardly find out if the image has been distorted or not. So in that way, even for uh, even for uh, even for audios, LSB works, but LSB introduces a lot of noise. So to avoid that, we actually use other things like there are other techniques like pulse and all those we saw in the slides. So which actually catches those regions wherein when I actually add the disturbance in the audio after I add the data is bare minimum, or the humans cannot actually find out if the data is there. The LSB part actually introduces a lot of noise in the signals, and humans can actually find out that okay, there's some disturbance in this and there is some data here. Unlike images, where images are just one pixel of the one LSB bit of the whole pixel value, hardly makes any difference. But audio has a lot of difference. Audio makes a lot of difference. So there are other techniques more popular compared to LSB for audio. Okay, and yeah, you can do this for video and you can do this for anything. Just we need to find out which part of the video, how do we represent it, how do we represent the video, how do we represent the audio, which part of the video, audio, or an image, when added, when the data is changed and modified, makes least difference to actually the audio or video, and then do the exact reverse to get the text back. Of course, we can add the keys to find out that actually to where the data is, how the data is spread. It's up to the implementer and the other person to actually encode and decode the data. Okay, so I've just shown you the audio one also, and I'll stop here. Thank you, sir. I stop, sir.
Yes.
Right,
So
sir.
students, we just learn a little better about steganography. So now that you have seen the Python code and the way he is doing things, I think things will be quite clear to you. So students, we'll stop here today and we'll meet on Thursday. Students, when is your exam starting? Mid-Feb?
Sir, 21st, sir. 21st Feb.
21st, sir.
21st. Okay, students. Today we'll stop here.
Thank you, sir.
Thank you.